Here's a short video on gas laws. You should already be familiar with the concept of pressure. If not, stop this recording and go back and learn about the units we use for pressure and what it is. Here is what we call the ideal gas law. If you're a chemist, you will remember this for the rest of your life. PV equals nRT. So what do these things stand for? Well, pressure is P, and it is measured in atmospheres, torrs, or millimeters of mercury in this class. The metric unit, or the SI unit for it, is kilopascals, and 1 atmosphere is about 100 kilopascals. The next unit is volume, and we usually use liters in chemistry. The metric unit is, of course, meters cubed, but we use liters very often in chemistry. N is the amount of gas, or the number of moles. Because we're chemists, we use moles. R is called the gas constant. The units and the value of this gas constant vary depending on the units you use for pressure and volume. But there are many different values for it that you can find very easily. And finally, temperature stands for T, or T stands for temperature. And the important thing to remember when you're talking about gas laws, we want to use Kelvin temperature. The reason for this is that these relationships between different parameters and the ideal gas law only works if you use Kelvin temperatures. There are a lot of sub-gas laws, but they can all be derived from pressure and or from the ideal gas law. So here we go. Let's look at the relationship between pressure and volume. Once again, using PV equals nRT. If we keep the amount of gas constant and its temperature, then nRT is a constant. So this whole item here becomes a constant. Why is this not working? Yeah, there we go. nRT is a constant. So we can rewrite this as PV equals a constant. So what does this mean? So if I just pull a constant out of thin air, let's just say that pressure times volume is equal to 300. So let's look at some values of pressure and volume if this is the case. Well, if the pressure is 300, that means the volume is 1. If the pressure is 150, then the volume is 2, and so on and so forth. As the pressure decreases, the volume increases. What this means is that pressure and volume are inversely proportional, meaning that the pressure is proportional to 1 over the volume, and the volume is proportional to 1 over the pressure. As one increases, the other must decrease. A good example of this is how we breathe. We are surrounded by about 1 atmosphere of atmospheric pressure, or 760 torr. And when we breathe, our diaphragm contracts. And what this does is it increases the volume inside our chest cavity. That makes the pressure inside our chest cavity lower than the atmospheric pressure. And so air rushes in. And this continues until the pressure is the same on the inside and the outside. At that point, our diaphragm relaxes, our lung capacity, or our chest capacity automatically lowers, and that makes the pressure inside of our chest higher than the outside pressure. And so air then leaves the body. But what's kind of hard for most people to understand is that if we weren't surrounded by atmospheric pressure, there would be no way that we could breathe. I mean, obviously, we couldn't get any oxygen, but we would increase the volume of our chest capacity, but there would be no mechanism by which air would be pushed into our bodies because there's no atmospheric pressure. This is a hard concept for people to get, but basically, to put it in a weird kind of non-chemistry form, there is no such thing as sucking. There's only blowing. So even when you're using a vacuum cleaner at home, we think of the vacuum cleaner sucking air and dirt up into the vacuum. But really what the pump is doing is creating a space where there are fewer gas molecules, where the pressure is lower. And so the atmospheric pressure is what is causing the air to rush into the motor. If there were no atmospheric pressure, vacuum cleaner would be pretty much useless. It wouldn't suck up anything. Let's look at the relationship between volume and temperature. Of course, we're still using an ideal gas, and we can use the ideal gas equation to do this. If we hold the amount of gas constant, so N, we're keeping N constant this time, and pressure, then we can rearrange this equation and look at the relationship between volume and temperature. To do that, we're going to get volume and temperature both on one side of the equation. Here's a little reminder of how to do that. We're going to take this equation and divide both sides by P. We want to get P over on the other side of the equation. So if we divide both sides by P, we end up with PV over P is equal to nRT over P. Well, P's cross out over here, and we end up with the volume is equal to nRT divided by P. We also want to get temperature over here on the side with volume, so we can divide both sides of the equation by T, and we end up with this. The volume over the temperature, or the volume divided by the temperature, is equal to nRT over PT. Well, of course, the T's will cross out too. But this is equal to a constant because we're not going to change the number of moles. We're not going to change the pressure. And so of course, R is not going to change. So what does this mean? Well, if we just pick a number and say that volume over temperature is equal to 5, and this is just for the purposes of explaining or showing you what this means. So here, if we say volume divided by temperature equals 5, if the volume is 5, that means the temperature is 1. If the volume is 50, the temperature is 10. And if the volume is 500, the temperature is 100. So this clearly shows that if you increase the volume, the temperature will also increase. This means that volume and temperature are directly proportional, meaning that if one increases, the other must increase. This little sign here is the proportionality sign. If you see that between two symbols, that means that they are directly proportional. If one increases, the other must increase, and if one decreases, the other must decrease. We can also look at the relationship between pressure and temperature by rearranging the equation, and we end up with something very similar to the volume temperature relationship. We get pressure divided by temperature is equal to nR over V. If we hold volume constant and we hold the number of moles constant, then pressure and temperature are directly related. So if the pressure increases, the temperature must also increase. So pressure is directly proportional to the temperature. Okay, let's take a quick minute here and check for your understanding. If it's a nice day out, the atmospheric pressure is about 1 atmosphere and the temperature is 298 degrees K. You're holding a balloon that has this initial size. What will the balloon look like if the conditions are changed? So you've got your balloon, and the day goes on and the temperature rises, but the atmospheric pressure stays the same. So an increase in temperature, pressure is held constant. What's going to happen to the balloon? is going to look more like A, B, or C. If you said that the balloon will look more like C than it did initially, you're correct. Temperature and volume are directly proportional. As the temperature rises, so will the volume. Okay, so you're back to your initial conditions, and you travel to the mountains where the atmospheric pressure is only 0.6 atmospheres. So the pressure is going to drop. So what happens to pressure or to volume when pressure decreases? Well, they're inversely proportional. So pressure if the pressure decreases by going up in the mountains, then the volume is going to increase. So once again, it's going to look more like the balloon C than it did initially. All right. Third set of conditions. You start out with your initial, and you open up the balloon and remove some of the air trapped inside. So in other words, you're lowering the amount of gas inside the balloon. Well, you guys should know this since like kindergarten, but in terms of chemistry, that means we are removing moles and volume are directly proportional. How do I know that? Well, let's go back one slide, see if I can. Well, let's just look at PV equals nRT, right? So we got PV equals nRT. See how bad this looks. Oh, so by the way, the answer is A. All right. So we said that pressure and volume are inversely proportional, but both pressure and volume are directly proportional to T. Math is our friend, and we can kind of garner some rules here. If we hold all this constant, then we said that pressure times volume means that they're inversely proportional. A little easier way to look at it is if they're on the same side of the equation, they're inversely proportional. Pressure and volume are inversely proportional. N and T are actually inversely proportional, but it's kind of hard to get the conditions right for that to happen. But anything on this side is going to be directly proportional to the parameters on this side. So volume is directly proportional to the number of moles, as is pressure. So if you open up the balloon and remove some of the air trapped inside, the volume is going to go down. And so the balloon will look more like balloon A. But this is one of those things that you know, but you didn't know you knew. All right. Standard temperature and pressure. We call it STP. It's a set of conditions that if you tell another scientist that you studied something at STP, they will know that you were talking about having a temperature of 273 degrees Kelvin or 0 degrees C and a pressure of 1 atmosphere. Now, the physicists will call this 100 kilopascals, but 1 atmosphere is good enough for us chemists. So what's interesting is that at STP, the volume of 1 mole of any ideal gas is 22.4 liters. This is about the same volume as a box that has dimensions of 11 by 11 by 11. And so it doesn't matter what gas it is as long as it's ideal. And most gases at laboratory conditions, or human conditions, I should say, if we could do it on a laboratory bench, most gases are ideal gases, at least at for the purposes of this class. So if we know the volume of a gas and the temperature and the pressure, we can figure out how many moles we have. And there is some stoichiometry that can be done using the volume of the gas to give us the number of moles instead of grams, which we use for dry chemicals, or concentration and volume, which we use for solutions. Anyhow, I hope this answers your questions. And of course, if you have any questions, please feel free to contact me.